Assalamu alaikum. Today we are going to explain Coulomb's law. Before this, we explain charges and its properties. We know that we have two types of charges. One type is positive and the other is negative. And when we close these charges experience some force which is called electric force. Now to calculate the magnitude of these forces, we can use Coulomb's law. The statement of Coulomb's law is the electric force between two point charges is directly proportional to the product of the magnitude of charges and inversely proportional to the square of the distance between them. Now let's come to know that what is mean by point charge. A charge object. A point charges lets we consider a charge object whose size is negligible. It means that whose size is very small as compared to the distance between other charges in the system. Now let's know about what is mean by point charge. Let we consider two cases. One is this and the other is this. In this case, the size of this charge, or we consider the size of this charge as compared to this distance, is very small. So we treat these charges as a point charges. And in this case, the size, let's the size of this charge or the size of this charge is larger as compared to the distance between them, and the distance between them is very small, so these are not point charges. Coulomb's law is applicable only for point charges which are stationary. Point charges are very small charges as compared to the distance between them. The distance between the charges is large. Now let's come to the mathematical proof of Coulomb's law. Electric force is directly proportional to the product of magnitude of charges, and electric force is inversely proportional to R square. Now let's combine these 2 points. Electric force is equal to Q1, Q2 and inversely proportional to R square. It means that if we increase charges, the electric force between the charges is increased, and if we decrease the distance, the electric force is increased. This is the distance between the point charges. Now let's convert this proportionality sign to equality. We put constant k here. F is equal to k q1 q2 divided by r square. Here k is Coulombic constant. In Coulomb's law, this k is called Coulombic constant and its value is equal to 1 divided by 4 pi epsilon naught. Here epsilon naught is the permittivity of free space. If we treat the charges in vacuum or free space, we write here F electric is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square. We know that charges are spherical, so this 4 pi term arises due to the spherical nature of charges. The value of Coulombic constant depends upon the nature of the medium between the charges and the system of unit which type of system we use, SI, MK, CGS, etc. In System International, the value of Coulombic constant K per vacuum is 1 divided by 4 pi epsilon naught is equal to 1 divided by 4. The value of pi is 3.14 and the permittivity of free space is 8.85 multiplied by 10 to the power minus 12. This is the value of permittivity of free space. Now if we calculate these values, we obtained the value of Coulombic constant 9 multiplied by 10 to the power 9 Newton meter square per Coulomb square, and this is the SI unit of Coulombic constant. Now let's come to know the permittivity. What is mean by permittivity? Permittivity is a material ability. It is the property of a material to hold or permit an electric field within itself. Generally, permittivity means that how much electrical energy, electrical field a material can store within itself. This property is called permittivity and it is represented by epsilon. For a material medium, it is represented by epsilon, and for vacuum or free space, it is represented by epsilon naught. Permittivity determines how much electrical energy a material can store when exposed to voltage or electric field. Materials with high permittivity. If we have a material and its permittivity is very high, act like a sponge for electric field. It means that it can store the external electric field within itself and affect the electric force between the charges. Air or vacuum has very low permittivity. If we take the permittivity of different medium, we we take the permittivity of air or vacuum is very low, very small. The electric field does not absorb or store if the permittivity is very small. Insulating materials like glass, rubber, etc., plastic has very high permittivity. These materials has very high permittivity. The materials absorb, so these material absorb and stores the energy, electrical energy from the electric field within itself, which which slow down or weaken the interaction between charges. It means that it affect if a material has very high permittivity, it reduces the electric force between the charges because some of the electric field is stored within the material. Now let's come to this example. Here this is positive charge and this is a negative charge, and we place insulator between these two charges. So due to this insulator, the force between this positive and this negative charges will be affected. It means it will be reduced because some of the electric field electrical energy is stored by this insulator within itself. Now let's calculate the dimension of Coulombic constant. We know that F is equal to K Q1 Q2 divided by R square. By cross multiplication, K is equal to FR square divided by Q1 Q2. Now let's calculate the dimension of force R Q1 and Q2 and put these value in this equation number 1. We know that F is equal to ma and acceleration is equal to v divided by t, v is equal to s divided by t, and now if we put the dimension of these terms, we take the dimension of forces ml per t square, and the dimension of r square is l square. We know that current I is equal to q divided by t. By cross multiplication, it is equal to q. The dimension of current is ARI and the dimension of time is T. Now put this value in equation number 1. We take the dimension of Coulombic constant as m L cube T to the power minus 4 A to the power minus 2, and this is the dimension of Coulombic constant. Enclose the dimension in these square bracket. Remember that. Dimension of permittivity. We know that we can calculate the dimension of permittivity directly from Coulomb's law. But easily if we remember the dimension of Coulombic constant, K is equal to 1 divided by 4 pi epsilon naught. Epsilon naught is equal to 1 divided by 4 pi K. Here 4 pi is a dimensionless constant. It means that this constant has no dimension. So we put the dimension of k directly here. Epsilon naught is equal to 1 divided by ml cube t to the power minus 4a square. If these terms move upward, then the dimension of permittivity will be equal to m to the power minus 1 l to the power minus 3 t to the power 4 a to the power 2, and enclosed this dimension in square bracket. Now let's come to know the Coulomb's law in a material medium. If we placed some insulating material medium between the charges, then what will be the effect on electric force? When we place an insulating material medium between the charges, it reduces the Coulombic force between the charges. If M is equal to electric force in a material medium is equal to K Q1 Q2 divided by R square is equal to 1 divided by 4 pi epsilon Q1 Q2 divided by R square. This is Coulomb's law in a material medium. If we place a material medium between the charges, here permittivity and force is inversely proportional. So if permittivity increases, electric force will be decreases. Here epsilon is the permittivity of a material medium. Relative permittivity or dielectric constant. What is mean by relative permittivity or dielectric constant, and it is represented by epsilon r, relative permittivity. The ratio of a material permittivity to the permittivity of a vacuum is called dielectric constant or relative permittivity. It measures how much electric field or electrostatic force is reduced when passing through that medium compared to vacuum. General formula for relative permittivity is epsilon r is equal to epsilon divided by epsilon naught. This is the permittivity of a material medium, and this one is the permittivity of free space, which is equal to 8.85 multiplied by 10 to the power minus 12. By cross multiplication, if we cross multiplication these two terms, epsilon is equal to epsilon r epsilon naught. For vacuum, relative permittivity is equal to 1. For vacuum or free space, the relative permittivity must be equal to 1. It means that relative permittivity can never be smaller than 1. For a material medium, relative permittivity is always greater than 1. It means that the relative permittivity for a free space or vacuum is equal to 1, and for a material medium, the relative permittivity will always be equal greater than 1. Relative permittivity or dielectric constant has no unit and has no dimension. There is no unit and no dimension of relative permittivity because it is a ratio between the two same physical quantities. Relative permittivity is also called specific inductive capacity. Now let's come to the Coulomb equation in a material medium. If m is equal to 1 divided by 4 pi, we place epsilon naught epsilon r in the place of epsilon q1 q2 divided by r square. Let's separate this term from this equation and this term. We know that this is the Coulomb's law in vacuum. So if m is equal to if v divided by epsilon r, relative permittivity is equal to if v divided by if m. This is the electric force between the two charges in vacuum, and this is the electric force between the two charges when a material medium is placed between them. Relative permittivity is also defined as the ratio of the force between two point charges in vacuum to the force between the same charges having same medium. Now let we know that the relative permittivity or dielectric constant of water is approximately 80. The relative permittivity or dielectric constant of water is equal to 80. Now put this value in the above equation. 80 electric force in water is equal to electric force in vacuum. Or we can write this equation: electric force between the two charges in water is equal to electric force between the two charges in vacuum divided by 80. In vacuum, the force between the two charges is 80 times larger as compared to water. In water, the force between two charges is 80 times smaller as compared to vacuum. Now let's explain these two situations. This is a positive charge and this one is negative charge, and there is no material medium between these two charges. There is only free space or vacuum between them. Now, these two charges will attract by an electric force. And the second situation is this one. This is a positive charge and this one is negative charge. And here we place water as a material medium between these two charges. So this equation means that as compared to water, the electric force in vacuum is 80 times larger. And this equation means that if we place water between that same charges and it same equal distance, but there is a material medium water. So here the electric force in water between these two charges will be reduced by 80. It means that it will be 80 times smaller as compared to vacuum. And this is our second lecture